Welcome to Nightauria. It's lovely to have you here tonight. Wherever you are right now, whatever corner of the world you've curled up in, I'm glad you found your way to this quiet little place. Maybe you're lying in bed with the blankets pulled up to your chin. Maybe there's a lamp still glowing somewhere across the room, the kind you keep meaning to turn off but never quite do. Maybe you're on a train or a couch or somewhere in between, with a cup of something warm slowly going cold beside you. It doesn't matter where. You're here, and that's enough. Before we begin, let me ask you something, just softly. Where in the world are you watching from tonight? I always wonder about that. Somewhere out there, it's the middle of the afternoon. Somewhere else, it's well past 3 in the morning, that strange and silent hour when the whole house seems to be holding its breath. If you feel like it, tell me down in the comments which corner of the night you're in and what time it is where you are. I read them. It's one of my favorite things, imagining all of you scattered across the planet, all settling in at once. And if you enjoy these slow journeys, if you'd like more nights like this one, a gentle like and a subscribe really does help this sleepy little channel keep going. Small creators like me rely on that more than you'd think. And to those of you already subscribed, who come back night after night, thank you. Truly, you're the reason this place exists at all. Now, here's the thing I should warn you about. I'm going to try very hard not to make tonight's story so interesting that it keeps you awake, but I can't make any promises. The thing we're going to talk about is genuinely one of the strangest, most quietly astonishing things that has happened in the history of human stargazing. And once or twice along the way, you might feel that little spark of wonder that makes you want to sit up. If that happens, well, at least you'll have learned something. A fair trade, I think, but mostly my hope is the opposite. My hope is that my voice becomes a kind of soft tide you can drift out on. So let me say this now clearly, so you can let go of any pressure you might be carrying. You do not have to follow every word. You do not have to understand every idea. There will be names and numbers and strange ideas tonight. And if any of them slip past you while your eyes are closing, that is perfectly fine. The ideas will still be here. They've waited billions of years after all. They can wait for you. If you fall asleep before the end, you've lost nothing. We'll move slowly. We'll take our time. There's no rush at all. Just let the words wash over you, one gentle thought at a time. So, settle in. Get comfortable. Let your shoulders drop away from your ears. And let me tell you about the night the sky did something it was not supposed to be able to do. I want to start with a single, quiet impossibility. A few years ago, an object passed through our solar system. A small thing in the grand scheme of things. And as it swung around the sun and began the long fall back out into the dark, away from us, away from all the warmth and light, it did something that should not have happened. It sped up. Now you might think, well, of course things speed up and slow down out there. The whole sky is full of motion, but this was different. When an object falls toward the sun's gravity pulls it faster and faster, the way a marble rolls quicker as it nears the bottom of a bowl. And then, as it climbs back out the other side, gravity tugs at its back, slowing it down again, the way that same marble loses speed as it rolls up the far side of the bowl. That's the rule. That's how it's supposed to work. Gravity gives and gravity takes back. The math is old and the math is reliable, and for a very long time we thought we understood it completely. But this little visitor didn't obey. As it left, it was going just slightly too fast. A tiny extra push, a faint nudge forward that gravity alone could not account for. It was as though something invisible had its hand on the object's back, pressing it gently onward out toward the stars. This wasn't a feeling or a guess or someone seeing a pattern that wasn't there. It was measured, carefully, painstakingly, by a team of astronomers led by a scientist named Marco Micheli and published in the journal Nature in 2018. They tracked the object's position night after night, plotting exactly where it should be if only gravity were acting on it, and then watching where it actually was. And the two didn't match. There was a real, undeniable extra acceleration. The thing was being pushed. Now here's where it gets strange, because in itself, an extra little push is not a mystery. We see it all the time. Comets do exactly this. A comet is, more or less, a great dirty snowball, a clump of ice and dust and frozen gas. When a comet swings near the sun, the heat boils that ice straight into vapor. It doesn't melt into a puddle the way ice does on a warm day here on Earth. Out in the vacuum of space, it goes directly from solid to gas, a process we call sublimation. And those jets of escaping gas act exactly like little rocket engines, hissing off the surface, nudging the comet this way and that. That's the visible push gravity can't explain. So when astronomers saw this object accelerating, the first sensible, obvious thought was, it's a comet, it's outgassing, mystery solved. Except when they looked at it, really looked, with the most powerful telescopes we had, they saw none of the things a comet is supposed to show. There was no coma. The coma is that soft, glowing halo of gas and dust that surrounds a comet's solid heart, the fuzzy cloud that makes a comet look like a smudge of light rather than a hard point. There wasn't one. There was no dust tail, none of that long, beautiful streamer of debris trailing behind, the thing we picture the instant someone says the word comet. None. And when they searched the light coming off the object for the chemical fingerprints of escaping gas, looking for the telltale signature of cyanide, of the usual molecules a comet sheds, they found nothing there either. No gas, no dust, no tail, no glowing halo. And yet, it was being pushed. Sit with that for just a moment, in the quiet. Here was an object behaving like a comet, with a comet's gentle extra shove, but showing absolutely none of a comet's exhaust. It was a chimney that pushed out smoke, but you couldn't see the smoke, couldn't smell it, couldn't find a single trace of it anywhere. A rocket with no visible flame. Something was clearly leaving that object, pressing it onward into the dark, and we could not find a single sign of what it was. That, my friend, is the small impossibility I wanted to start with. That is the loose thread, and tonight, very slowly, we're going to pull on it. Because to make any sense of this strange, silent push, we have to understand what this object even was and where it came from, and we have to meet not one, but 3 extraordinary visitors that have arrived at our doorstep in just a handful of years. And by the time we're done, you'll understand something rather beautiful. You'll understand why 2 of these 3 visitors turned out to be exactly what we expected, and why the third, this pushed and silent one, remains, to this very day, a mystery we genuinely cannot solve. But I'm getting ahead of myself. We have all night. Let's slow down. To understand just how strange these visitors are, I want to take you back, way back, to a time before any of this happened. Not very far in years, but in a way, a whole world ago. Before the autumn of 2017, the universe, as far as our records were concerned, was a very tidy place. We had our planets, the familiar family of worlds circling the sun. We had our asteroids, those rocky leftovers, mostly tucked into a great belt between Mars and Jupiter. We had our comets, the icy wanderers that swept in from the cold outer reaches and then looped back out again, faithful as clockwork, bound to the sun by invisible chains of gravity. Everything in the sky that we knew of belonged to us. Everything we had ever catalogued, every rock and every snowball, every speck of dust we had ever named, had been born here in our own solar system, spun out of the same swirling cloud of gas and dust that made the sun and the earth and you and me 4.5 billion years ago. It was, in a sense, a closed house, a family that had never had a visitor walk in through the front door from outside. We had always suspected, of course, that other stars must have their own families too. Other suns with their own planets, their own asteroids, their own comets. And we reasoned, quite sensibly, that some of those distant objects must occasionally get flung out into the space between the stars, set loose to drift across the unimaginable gulfs of the galaxy. We assumed such wanderers existed. We just had never, not once in all of recorded history, in all the thousands of years that human beings had looked up and watched and charted the heavens, actually caught one passing through. They were a thing we believed in but had never seen. Like footprints we were sure must exist, on a beach we had never been able to reach. So settled was this picture, so complete did it feel, that we didn't even have a name for such a thing. We had categories for everything we knew. Asteroids had their designations, comets had theirs, but for an object that came from another star entirely, that fell in from the dark between the suns and would leave again, never to return, there was no category at all, no label, no box to put it in. The very idea was so far from our daily experience that the great international body that names these things, the International Astronomical Union, simply had no system ready for it. And then, in October of 2017, the front door opened. When that first visitor was confirmed, when astronomers realized with a kind of breathless certainty that they were looking at something that had truly come from beyond, the naming union had to act, and act fast. They invented a brand new class of object then and there, almost overnight. They gave it a letter, the letter I for interstellar, between the stars. A whole new branch of the family tree, sketched in real time because reality had outrun our paperwork. The first of these objects was given the designation 1I, the very first, number 1 in a category that the day before had not existed at all. Think about that just for a moment as you lie there in the dark. You are old enough to remember a time when humanity had never knowingly touched a piece of another solar system. And then quite suddenly we had. A whole new kind of thing entered the human story, and a new word had to be carved out to hold it. We weren't reading about old discoveries in a dusty book. We were watching a fresh page of astronomy being written, the ink still wet. That doesn't happen very often. We're lucky, you and I, to be alive in the years it did. But I can hear the careful part of your mind, the part still gently awake, asking the obvious question. How? How could anyone possibly know that this object had come from another star? It's not as if it arrived carrying a passport. It's not as if it had a return address stamped on its side. It was just a faint dot of light, far away and moving fast. So how did they know with such confidence that it wasn't simply some ordinary rock from our own backyard that we'd never noticed before? The answer is one of those moments where the universe gives us a clean, honest signature, written in the plainest possible language, the language of motion. And the signature is something called eccentricity. Let me explain it gently because it's lovely once you see it. Every object that orbits the sun travels along a particular kind of path, a particular shape, and we have a single number that describes that shape. We call it the eccentricity. It tells you how stretched out, how elongated an orbit is. And if an object travels in a perfect circle around the sun, going round and round at exactly the same distance forever, its eccentricity is 0, perfectly round. Now, almost nothing travels in a perfect circle. The planets travel in paths that are very slightly squashed circles, what we call ellipses, ovals, just a little bit stretched. So they have eccentricities a little above 0. Comets, the long-range ones, travel in much more dramatically stretched ovals. They swoop in close to the sun and then swing far, far out before falling back, so their eccentricities can climb quite high, getting closer and closer to one. But here's the crucial thing, the thing this whole story hangs upon. As long as an object is truly bound to the sun, as long as it belongs to us and will loop back around again someday, no matter how stretched its orbit, its eccentricity stays below 1. Below 1 means a closed loop. Below 1 means it's family. It might take 1,000 years to come back, it might take 1,000,000, but it will come back. It's on a leash, however long. The sun has a hold on it. The moment an object's eccentricity reaches 1 and then goes past 1, climbs above 1, everything changes. An eccentricity above 1 no longer describes a closed loop at all. It describes an open path, a path that comes in, sweeps around the sun once, and then leaves forever, never to return. We call that kind of open one-way path a hyperbolic trajectory. And a hyperbolic path means one thing and one thing only. This object is not bound to the sun. The sun never captured it. It was never ours. It came in from somewhere else, falling freely through the dark. And after its single brief visit, it is going back out into the deep. And we will never see it again. So eccentricity is the passport, after all, not stamped on the object's side, but written in the curve of its path through space. And when the astronomers measured the path of that first visitor, in 2017, the number they got was about 1.20 above 1, comfortably, unmistakably above 1, not by some tiny, arguable fraction that might be a measurement error, solidly past the line. This thing was on an open road, just passing through, on its way to somewhere we cannot follow. And here is the part I love, the part that makes this proof feel so solid you could lean your whole weight against it. This wasn't a one-time fluke, because as we'll come to, 2 more visitors followed, and each of them carried the same passport, only written even more boldly. The second visitor had an eccentricity of about 336, far, far above 1, and the third, the most recent arrival, had an eccentricity even higher than that, reported above 6. 6. These are not the gentle, almost closed ovals of objects that belong to us. These are wild, wide-open, screaming fast hyperbolic paths, the trajectories of things that fell toward our sun from immense distances, looped around it once like a stone whipped around on a string and then let go, and are now climbing back out into interstellar space, gone for good. The sun could not hold any of them. They were only ever passing through. The numbers don't lie, and they don't leave room for doubt. These objects came from other stars. We are certain of it. Of all the strange and contested things we'll talk about tonight, that one fact is bedrock: they are not ours, they came from out there. Now that we know how we can be sure of where they came from, let me properly introduce you to the first one, the one that started all of this, the one being pushed by something invisible. It was discovered on the 19th of October in the year 2017. It was found by a telescope called Pan-STARRS-1, a great watchful eye perched high atop a mountain called Haleakalā on the island of Maui in Hawaii. Haleakalā is a place of thin, clear air far above the clouds, where the sky at night is so dark and so deep that it seems to go on forever, and the stars hang close enough to touch. A good place to keep watch. The telescope's job, night after night, is to sweep across the heavens looking for anything that moves, anything new, any faint point of light that has shifted since the night before. Most of what it catches is ordinary. Known asteroids, drifting comets, the familiar traffic of the inner solar system. But on that October night, it caught something that didn't fit. A faint dot moving far too fast on a path far too steep. A path that, when they worked it out, turned out to be that open hyperbolic curve. a path that could only mean one thing. In keeping with where it was found, the astronomers in Hawaii gave it a Hawaiian name. They called it ʻOumuamua. It's a beautiful word, and it carries a beautiful meaning. It means, roughly, a messenger from afar arriving first, a scout, the one sent ahead. And wasn't that exactly right? Here was the first of its kind we had ever knowingly seen, a messenger that had traveled across unfathomable distances, across the cold and empty space between the stars, for who knows how many millions or billions of years, to arrive at last at our small and ordinary corner of the galaxy. The first to be caught, the scout, ʻOumuamua. Even its formal catalogue name carried that proud little number. 1I, the first interstellar object, the very first. And so this messenger from afar slipped quietly into our solar system, swung around our sun, and began its long journey back out into the night. And as it left, it sped up, just slightly, pushed by something we could not see. No coma, no tail, no gas, no dust, just a small, silent, impossible nudge, carrying it home to the stars. That is where our story truly begins. With a quiet impossibility, a messenger that arrived first, and a push that no one could explain. And I promise you, the more we look at this small and lonely object, the stranger it becomes. We've only just met it. We haven't yet talked about its shape, which is unlike anything we have ever seen. We haven't yet talked about the way it tumbled through space, or its strange reddish color, or the most painful fact of all, the reason this mystery may never, ever be solved. And we certainly haven't yet met its two siblings, the two visitors who arrived after it, the two who turned out to be so reassuringly, beautifully ordinary that they only make ʻOumuamua seem stranger by comparison. But all of that is still ahead of us. We have plenty of night left. So for now, just rest here a moment, in the quiet, with the image of it. A small, dark, reddish object, no engine, no flame, no visible breath of gas, tumbling slowly end over end as it falls away from our sun and back out into the endless dark, carrying its secret with it. Speeding up. Just slightly. For reasons we still, to this day, do not fully understand. Let that picture settle softly in your mind, and let's keep going, slowly, into the strangeness of the scout. Before we go any further into the strangeness, let me say a quiet welcome to you. Welcome to Nightoria. Wherever you are tonight, whatever the hour is in your corner of the world, I'm glad you're here. And I'm genuinely curious, so if you feel like it, leave a little note below and tell me where you're listening from. A city, a country, the view from your window. I love reading them, even if you're half asleep when you write it. And if these slow journeys into the night help you drift off, a gentle like and a subscribe really do help this small channel keep going. Small creators like me lean on that quiet support more than you know. So thank you truly to everyone already here. And to anyone new, settle in. There's no rush at all. Because that's the thing about tonight. There is nothing here you need to hold on to. Nothing to memorize. No equations to follow. No test at the end of the night. If your eyes grow heavy and you slip away somewhere in the middle of all this, that is perfectly fine. The story will still be here, waiting, just as it has waited for billions of years to be told. We're going to move slowly through it, one quiet idea at a time, the way you might walk through a dark and beautiful house, pausing at each room, in no hurry to reach the end. So loosen your shoulders, let the blanket settle, and let me carry the thinking for a while. Now, to really understand why that small, silent push mattered so much, you have to understand the world as it was before any of this happened. You have to understand how settled things felt. Because before the autumn of 2017, the kind of object we're talking about tonight did not officially exist not in our catalogues, not in our naming systems, not in the tidy way astronomers like to organize the sky. We had asteroids, those dry, rocky bodies that loop around our sun. We had comets, the icy ones that grow their glowing tails as they approach the warmth. And we had a few smaller categories in between, but all of them, every single one, belonged to us. They were born here in our own solar system from the same cloud of dust and gas that made the sun and the earth and you. They were family. They never left, and nothing from outside ever came in. Or at least, nothing we had ever caught. There was no class of object for a visitor, no label, no box, no name, for a thing that drifted in from another star entirely. The very idea was a kind of beautiful, theoretical maybe, something astronomers suspected must happen out there in the vastness, but had never once seen with their own instruments. The sky, for all its mystery, felt complete in this one quiet way. A closed garden with a wall around it that nothing ever crossed. And then, almost overnight, that wall came down. ʻOumuamua forced the people who named these things, the International Astronomical Union, to invent something brand new right then and there. They had to create an entirely new class of object, marked with a capital letter I for interstellar. A whole new branch of astronomy, born in a hurry, because reality had just handed us something our old categories simply could not hold. That little eye is the sound of a door opening in a wall we thought was solid. We were, quite literally, watching a new chapter of science begin in real time because one small dark object refused to belong to us. But how, you might gently wonder, drifting there in the dark, how could anyone possibly be sure? How do you look at a faint smudge of light, hundreds of meters wide, already racing away from you, and declare with confidence that it came from another star? Not from some distant corner of our own system, but from somewhere else entirely. That feels like an enormous thing to claim from so little. And here is where the story becomes solid. Because the proof, it turns out, was hiding in the shape of its path, in the curve of how it moved. Let me explain it as softly as I can. Everything that truly belongs to our sun travels in a kind of loop, a closed path. The Earth loops around the sun every year and comes back to where it started. A comet might take thousands of years, but eventually it too comes back. They are all caught, all held, all bound by the sun's gravity, like a ball on a very long string, always swinging back around no matter how far it flies. Astronomers have a single number to describe just how stretched out one of these loops is. They call it the eccentricity. And here is the only piece of arithmetic you need to carry into your sleep tonight, the gentlest little rule for anything truly bound to our sun, anything that will come back. That number stays below 1. Below 1 and you belong here. Below 1 and you are family. ʻOumuamua's number was about 1.2, just above the line, just over the edge. And that small difference changes everything. A number above 1 doesn't mean a stretched out loop. It means no loop at all. It means a path that is open, that comes in once, swings around the sun, and leaves forever, never to return. The mathematicians have a word for that kind of open curve. They call it hyperbolic, a one-way visit, a trajectory that the sun, for all its enormous pull, could never bend back into a circle, could never capture, could never keep. ʻOumuamua simply passed through, the way a stranger walks through the light of a street lamp and continues on into the dark on the other side. And once you understand that, the whole thing clicks quietly into place. This object was never ours. It fell in from the space between the stars, took one long, graceful turn around our sun, and is right now sailing back out, gone for good. The number told us so. The math gave us the proof that our eyes never could. And later, when its two siblings arrived, that same simple test would give the same simple answer, only louder. The second visitor would carry a number of around 3.3. The third, even higher still, well above 6. Each one more steeply hyperbolic than the last, each one screaming the same truth in clearer and clearer letters. Not from here, not ours, just passing through. So now you can feel the full weight of that opening moment. A faint point of light caught for the very first time on the night of October the 19th, 2017, by a patient telescope called Pan-STARRS-1, perched high on the slopes of the Haleakalā Observatory on the island of Maui. The astronomers there reached for a name, and they chose a Hawaiian word, ʻOumuamua. It means, roughly, a messenger from afar arriving first, a scout. And what a perfect name it turned out to be. The first of its kind, the one that arrived ahead of all the others and opened the door. The scout sent on ahead into the warm light of an unfamiliar sun, only to be noticed just as it was already turning to leave. So rest there with me a moment longer in that strange and lovely truth. A messenger, named before we understood it. A path that proved it could only have come from another star. And a quiet, mathematical fact, a single number just over the line that turned an impossible idea into something certain. We hadn't simply found a new rock. We had received our very first piece of mail from somewhere else, postmarked from a star we may never even be able to name. And now you get to meet it properly. Now that you understand why it matters, now that the number and the proof and the name are settled in your mind, we can slow down a little and simply look at the thing itself, or as close to looking as we can manage, which is to say, we can look at what the light told us, because light was all we ever had. ʻOumuamua was small, probably. The honest answer to almost every question about its physical appearance starts with that word, probably, and you'll understand why by the time we're done here. But the best estimates put its longest dimension somewhere between about 100 meters and 400 meters. If you're lying in bed trying to picture that, think of a skyscraper, a tall one, maybe 30 or 40 stories. Something like that, though the precise truth is we were never entirely sure because we never actually saw it, not directly. What we saw was what it did with sunlight, which is a different and considerably more frustrating thing. As it tumbled through our inner solar system, ʻOumuamua caught and reflected light from the sun the way any rock does, except that the amount of light we received from it kept changing dramatically. It would brighten, then fade, then brighten again, and the rhythm of that brightening and fading had a period of roughly 8 hours. A long, slow tumble, a single slow rotation every 8 hours or so, end over end, or maybe side to side, the precise axis shifting and precessing in a way that suggested not a clean spin, but a kind of chaotic, unsettled wobble. Astronomers call that tumbling. The object is rotating, yes, but not stably, not the way a top spins in a single clean plane, more like a piece of wood thrown into the air, flipping and rolling and turning all at once, more restless than that, uncertain in its motion. Now the fact that it tumbled was interesting, but not unusual. Plenty of asteroids tumble. What was unusual was how much the light changed. The brightness swung by a factor of roughly 10 across a single rotation, 10 times brighter, then 10 times fainter, over and over, with every turn of that 8-hour cycle. In the language astronomers use, that's a change of about 2.5 magnitudes, which sounds technical, but is really just a more precise way of saying the same thing. It dimmed to nearly nothing, then blazed back up, and the ratio was extreme. More extreme, actually, than anything ever measured for a solar system body at the time. The most dramatic light curve swing ever recorded for any asteroid, any rock, anything. This was not a normal spinning rock. Something about its shape was profoundly different. And here is where the picture starts to get strange and beautiful and contested all at the same time. Because when you see that kind of light variation, that wide and regular a swing, what you're really seeing is the shape of the object written in light. A perfectly spherical object wouldn't vary at all. It's a sphere. Every angle looks the same. But an elongated object, something much longer in one direction than the others, something that presents a large face to you and then a narrow edge and then a large face again as it rotates, that would produce exactly this kind of swing. Bright when you see the broad side, faint when you see the narrow end, and the bigger the difference between broad and narrow, the bigger the swing in brightness. 2.5 magnitudes implies something extraordinary about the proportions. The first calculation suggested an axis ratio of about 6:1, 6 times longer in one direction than the other. Then some models pushed it further to something like 10:1. Either way, nothing in the solar system comes close. A ratio like that, if it describes an elongated object, gives you something shaped roughly like a cucumber, but elongated far beyond any cucumber you've ever eaten. A pencil, more like. A needle. The first images people reached for were of a cigar, a long tumbling cigar, and for a while that was the description that stuck. It spread through news coverage, into magazine illustrations, into the public imagination, and honestly, it's a vivid image, and not wrong exactly, just not the whole picture either. Because it turned out that the cigar was only one possible interpretation. A long, thin shape would create this brightness variation, yes. But so would something else entirely. A flat, wide, thin shape. A disc, a pancake, a leaf. If you hold a coin edge on, it nearly disappears. Turn it face on and it fills your field of view. That transition from edge to face and back again would also produce a dramatic light swing. And when researchers looked more carefully at the data, at the precise timing of the brightness changes, at how the curve rose and fell, some of them found that a flat, thin disc actually fit the observations as well as or better than the long cigar. Maybe better. The shape was never resolved. The debate between elongated rod and flattened disc remained live throughout everything that followed, and it matters more than you might think because, as we'll see, the shape became evidence in an argument much larger than shape. For now, just hold both possibilities gently. A body that is either very long and thin or very flat and wide, and almost certainly more extreme in its proportions than anything we have in our own solar system. Already it was unlike the objects we're used to, and it was only just getting started. Its color was a faint reddish orange. Not dramatically red, but noticeably ruddy, a warm tan, the kind of hue you sometimes see on objects in the outer solar system, things that have been sitting in the cold and the dark for a very long time, with the thin wash of cosmic radiation slowly doing its work on their surfaces. This process is called space weathering, and the particular kind of reddish organic molecules it tends to produce over long timescales are called tholins. When you see that color on an asteroid or a comet, you're seeing the marks of age and distance. A surface that has been slowly cooked and reddened over millions, possibly billions of years by the low hum of radiation streaming through interstellar space. It was one of the few things about Oumuamua's composition that felt, in a strange way, familiar. This reddish weathering we understand, we've seen it before. It speaks of a long journey through deep space, which made sense given what we knew. It had come from somewhere very far away, and that journey takes time, and time leaves marks. But here is the thing about all of this, all of the shape and the color, and the tumbling and the size estimates, all of it came from a single source of information. The light, just the light, because we never got close to it. No spacecraft flew past, no camera zoomed in, no probe was waiting. We had telescopes on the ground and one powerful space-based tool, and we pointed them at a fading point of light moving fast against the background stars, and we extracted everything we could From the way that point brightened and dimmed, everything you've just heard about its shape and its color and its tumbling was inferred, calculated, modeled from those observations. We never saw the object itself. We saw its shadow in the data. The Spitzer Space Telescope tried to help. Spitzer was a remarkable instrument, sensitive to infrared radiation, which is to say, heat. It could pick up the warm glow of a body even when that body was too small or too dark to be easily seen in visible light. Astronomers pointed Spitzer at the position where ʻOumuamua ought to be in the weeks after its discovery, hoping to measure its thermal emission and get a better fix on its size and surface properties. What Spitzer found was nothing, no detection at all, which in science is not nothing because an absence of signals still tells you something. It told us that ʻOumuamua was either smaller than our best guesses or more reflective or producing very little dust, or some combination of all three. The Spitzer non-detection tightened the constraints, narrowed the possibilities, forced the models to adjust. It was another piece of data pulled from absence, another measurement made not from what was found, but from what wasn't. Even the silences were full of information, if frustrating information. And then there's the question of why we had so little time to look. This is the part of the story that I find almost unbearably poignant, and I hope you'll feel some of it too, even half asleep here in the dark. Because here's the thing that changes the emotional register of everything else. ʻOumuamua was not discovered as it arrived, it was discovered as it was leaving, already on its way out, already past its closest point to the sun, already past its closest approach to Earth, already accelerating away. The night of October the 19th, 2017, when Pan-STARRS 1 first caught it, it was already outbound. The closest, brightest, most observable moment was in the past. Scientists who wanted to study it were working against an ever-fading signal, a retreating object growing fainter with every night that passed. The window was roughly 2 to 3 weeks, maybe a little longer for the largest telescopes, which could hold on a bit further. But the object was moving fast and it was moving away, and there was nothing to be done about that because there is no way to ask a rock from another star system to slow down and wait. By the time the international astronomy community fully understood what they were looking at, the chance was largely spent. And then it was gone. Not gone in the way a comet gets faint and comes back around the next perihelion. Gone permanently. An escape trajectory, remember? Eccentricity of 1.2. It is not orbiting the sun, it never will. It passed through once on a long hyperbolic arc that brought it in from interstellar space and will carry it back out into interstellar space, and it is now on its way to somewhere else, some other long emptiness between stars, and it will never come back. Every telescope that was used to study ʻOumuamua was improvised, pointed on short notice at a moving target that was already shrinking in the sky. The data that exists is the data that could be gathered in those few weeks by instruments that were not designed for this kind of target, in conditions that were sometimes far from ideal. And from that slender record, that thin sheaf of photographs and spectra and photometric curves, we are expected to understand something wholly new. We can't go back. There's no sample, no close-up image. The witness left the room while we were still introducing ourselves. And because of this, and only because of this, the central question about ʻOumuamua can never be definitively answered with the evidence we have. It is not that scientists disagree out of stubbornness or political preference or scientific tribalism, though those things exist in science like everywhere else. It is that the data genuinely cannot, on its own, distinguish between several competing explanations. The honest position is that we do not know, and we cannot know from the data we collected. And this is simply a fact about the universe being uncooperative, about a visitor arriving when we weren't ready and leaving before we were satisfied. So, With all of that in mind, let's look at the explanations. Because there are several, and they're serious, and they deserve your attention, especially here in the quiet of the night, when nothing is rushing you anywhere. The central mystery, the one that electrified the scientific community after the discovery, was not the shape or the color or the tumbling, though those were all interesting. It was something far more specific and far more hard to explain. It was the fact that ʻOumuamua accelerated. As it moved away from the sun after its closest approach, its trajectory didn't behave the way a simple, inert rock's trajectory ought to behave under gravity alone. It moved slightly faster than the math of gravity could account for. The acceleration was small, subtle, nothing you'd feel if you were riding on it. But, from the outside, tracking it against the background stars, it was measurable, clear, and it was measured, carefully and rigorously, by a team led by Marco Micheli, whose analysis was published in the journal Nature in 2018. The non-gravitational acceleration was real. It was not a measurement error, it was not a computational artifact. It was in the data, it had been looked at carefully from multiple angles, and it was there. Now, when a comet does this, we don't blink. Comets have gas and ice mixed into their interiors, and as they warm near the sun, that material boils off into space, and the escaping gas acts like a tiny rocket exhaust, pushing the comet slightly off the purely gravitational path. We call this outgassing, and it produces the coma, that hazy cloud of gas and dust that surrounds the nucleus of an active comet, and the tail, that spectacular stream of material blown back by solar wind. It's a beautiful thing. We understand it. It's physics. The comet is its own propulsion system, consuming itself as it moves, and the pressure of that self-consumption nudges its path. The problem, the maddening and deeply strange problem, is that ʻOumuamua showed this acceleration but displayed absolutely none of the associated evidence of outgassing: no coma, no tail, no detectable gas. The most sensitive instruments available searched for cyanide, a molecule comets routinely produce, and found nothing. Astronomers looked for any sign of dust being blown off, of gas streaming away, of the usual cometary performance, and found silence. The object was pushing itself like a comet while producing no exhaust anyone could detect. A car accelerating without a running engine, a kettle whistling with no steam rising from it, the effect unmistakably real, the cause completely invisible. This is the anomaly, and it is why ʻOumuamua sits in a category of its own, even among interstellar objects even today, because the other two visitors we've received don't have this problem, as you'll discover later in the night. They behaved exactly as expected, this one didn't. And from the attempt to explain this one misbehaving fact, an extraordinary range of ideas emerged. The first serious natural explanation that got significant attention is the hydrogen iceberg hypothesis. It came from Darrell Seligman and Gregory Laughlin, proposed in 2020. The idea goes like this. What if ʻOumuamua were made not of the rocky or icy materials we normally associate with asteroids and comets, but primarily of solid molecular hydrogen? Frozen hydrogen, H2, the simplest molecule there is. At extraordinarily cold temperatures, hydrogen gas can condense into a solid. If ʻOumuamua were a large chunk of this substance, then as it passed close to the sun and warmed, the hydrogen on its surface would sublimate, meaning it would transition directly from solid to gas without going through a liquid phase, and that escaping hydrogen would push it. That's the outgassing mechanism, still operating, still responsible for the acceleration. But here's the key. Hydrogen gas, when it escapes into space, is essentially transparent and extremely hard to detect with the instruments we typically use to look for cometary emissions. We wouldn't necessarily see it, not because it wasn't there, but because it was the wrong kind of exhaust for our detectors to catch. A comet exhaust you can't see. a perfectly invisible rocket from the perspective of our telescopes, the numbers worked out reasonably well. The acceleration was about the right magnitude for what you'd expect from a body of roughly that size sublimating hydrogen at roughly that rate near the Sun. It was an elegant solution. Not satisfying in a simple way because it involved a kind of object that nobody had ever seen or really expected, but elegant in the sense of fitting the available evidence without requiring anything obviously impossible. But then came the counter-argument from Thiem Hoang and Avi Loeb, also in 2020. And the counter-argument was this: solid molecular hydrogen is extraordinarily fragile. Not fragile the way glass is fragile, physically delicate, likely to crack. Fragile in the sense that it's thermally fragile, energetically fragile. The interstellar journey that ʻOumuamua took, traveling between stars, exposed to the constant low-level hiss of cosmic radiation and the ultraviolet light of distant stars, would have delivered enough energy to the surface of an H2 iceberg to erode it considerably. The question became whether such a body could survive the transit intact, whether it could form in the first place, large enough to make the journey without sublimating away. The math on this was not encouraging. An H2 iceberg would have a very hard time being produced in nature in dimensions large enough to match what we observed, and would have an equally hard time surviving the long, cold journey between stars. It might simply evaporate away long before it ever reached a new solar system to confuse the astronomers living there. And so the hydrogen iceberg, while not ruled out entirely, became a disputed option. Another piece of the puzzle that fit some faces of the box, but not all. Then there was a second natural explanation, and this one has a kind of poetry to it that I find particularly beautiful. In 2021, Steve Desch and Alan Jackson at Arizona State University proposed what has sometimes been called the nitrogen iceberg hypothesis, or more colorfully, the cosmic Pluto idea. The argument begins at the edge of our own solar system with bodies like Pluto. Pluto's surface is covered with frozen nitrogen, solid N2. It's one of the things the New Horizons probe revealed when it flew past in 2015, that remarkable close-up look at a world we'd never seen clearly. Pluto gleams in part because of this nitrogen ice, which is highly reflective, and in other solar systems around other stars, there would presumably be similar worlds. Cold, distant, nitrogen-covered bodies hanging at the outer edge of their systems. Now imagine that one of these Pluto-like worlds, somewhere around another star, was involved in a collision or was struck by something large, and in that impact, a fragment was ejected. A chip of the nitrogen ice surface, blown off by the violence of the collision, cast out at a high enough velocity to escape the gravitational pull of its home system. That chip, now drifting alone through interstellar space, is mostly frozen nitrogen. When it eventually wanders into a new solar system like ours and heats up near a new star, the nitrogen sublimates. And here's the elegant part. Nitrogen, like hydrogen, sublimating from the surface would push the object in a way consistent with the acceleration we measured. And also like hydrogen, nitrogen sublimation doesn't produce the highly visible dust and gas signatures we'd normally associate with cometary outgassing. The exhaust is there, it's physically doing its work, but it's not presenting itself to our detectors in the ways we'd expect from a typical comet. There's one more appealing feature. Solid nitrogen is highly reflective, as mentioned. If ʻOumuamua were coated or largely composed of bright reflective nitrogen ice, that would help explain why the Spitzer Space Telescope didn't pick up significant thermal emission. A highly reflective object doesn't absorb much sunlight and doesn't radiate much heat. The Spitzer non-detection fits. The brightness fits. Even the reddish color could be explained by a thin layer of radiation-processed surface material on top of the nitrogen body beneath. The model does a lot of work with a single ingredient. But the nitrogen iceberg also attracted criticism. Avi Loeb, together with Amir Siraj, did some arithmetic about how many nitrogen chip objects of the right size would need to exist in the galaxy to explain our catching one on the very first search. Because here's the thing, if interstellar objects are rare, catching one quickly is unlikely, but if they're common, any particular explanation needs to account for why they're common enough to be caught that easily. The numbers Loeb and Siraj ran suggested that producing enough nitrogen chunk objects to match the implied population rate would require more nitrogen than the galaxy seems plausibly able to supply in that form. You'd need an enormous number of Pluto-like worlds having enormous numbers of collisions, chipping off enormous numbers of nitrogen fragments, and then somehow all of those fragments surviving long enough to drift around interstellar space in sufficient numbers that we happen to catch one in our first few years of looking. The nitrogen hypothesis under this scrutiny seemed to require a galaxy that's unusually generous with a particular material in a particular form. Possible, perhaps, but the numbers feel strained, and so the nitrogen iceberg, like the hydrogen iceberg before it, carries explanatory appeal and stubborn difficulties in roughly equal measure. A third class of explanations involves something a little different. Rather than imagining ʻOumuamua as a solid body of some unusual ice, some researchers suggested it might be something more loosely assembled, a fractal dust aggregate in the technical language. Imagine something like a snowflake, but far larger and constructed over long time scales in the cold of interstellar space, where tiny grains of dust and ice slowly accrete and stick together in a diffuse, lacy, porous structure. Not a solid, compact body, but something more like a very large, very loose cloud of particles clumped together with enormous amounts of empty space between the actual material. The density of such an object could be astonishingly low, much lower than any ordinary rock. Now, sunlight exerts a real physical pressure. This is not a figure of speech. Photons, particles of light, carry momentum, and when they bounce off a surface, they transfer that momentum to the surface. For an ordinary rock or asteroid, this radiation pressure is so tiny compared to the object's mass that it's essentially irrelevant. You can ignore it. But for something extremely low in density with a very large surface area relative to its mass, the calculation changes. If ʻOumuamua were fluffy enough, porous enough, spread out enough relative to its mass, then the ordinary pressure of sunlight might be sufficient to push it in the way we observed. No exhaust at all, just light. The same force that slowly deflects spacecraft over decades through the Yarkovsky effect, acting more dramatically on an object that is almost more gap than matter. Something less like a rock and more like a very large, very sparse tumbleweed drifting in a sunlit wind. This also explains the lack of visible outgassing neatly, because there is no outgassing. The light is doing all the work, and a porous, loosely structured aggregate might not produce much in the way of thermal emission either, which could explain the Spitzer non-detection. It might reflect light oddly, consistent with the extreme brightness variations. The pieces fit. Not all of them perhaps, not in every detail, and constructing such an object naturally in the interstellar environment involves its own set of questions about how stable it would be and how it would behave over long time scales. But it's a serious proposal, not a fringe idea, and it belongs alongside the icebergs in the honest catalogue of what we considered. And then, running alongside all of these, there's a simpler possibility that keeps getting raised in quieter tones. What if it was just outgassing after all? What if ʻOumuamua was venting some volatile material, some gas below or near our detection thresholds, and we simply didn't have instruments sensitive enough or well-positioned enough to catch it? Perhaps carbon monoxide or molecular hydrogen produced by some photochemical process on the surface, or some other trace volatile we hadn't thought to look for in quite the right way. The absence of a detection doesn't mean zero, it means less than whatever limit our instruments could resolve. and our instruments, scrambled into action on short notice to watch a fast-retreating target, were not operating at their theoretical best. The measurement limits were real, and below those limits was a space of possibility we couldn't explore. Each of these explanations, the hydrogen iceberg, the nitrogen chip, the fractal aggregate, the below-threshold outgassing, has something going for it. Each has something it struggles to explain. None fits perfectly. And if you're looking for the scientific consensus on which one is right, I have to be honest with you, there isn't one. The planetary science community has not converged. Probably the majority of researchers lean toward some kind of natural explanation involving unusual composition or structure, which is the sensible default position, the application of parsimony. An unusual object from another star system might well have unusual properties. Nature is stranger than our local sample suggests, but the specific mechanism remains genuinely open, all of which brings us to the explanation you've probably heard about, the one that generated the most headlines and the most controversy, and, depending on your disposition, either the most excitement or the most eye-rolling. But we'll arrive there in good time. For now, just rest here with the strangeness of what you've already been given. An object the size of a skyscraper, possibly shaped like a disc or a needle, tumbling once every 8 hours in a restless, precessing wobble. The color of old, tarnished rust, accelerating away from us without visible exhaust, discovered already leaving, gone in weeks, never photographed up close, never understood completely, and now surrounded by a careful, serious, still unresolved argument about what it could possibly have been made of, an argument that cannot be won because the evidence runs out exactly where the crucial answer would begin. That's ʻOumuamua in all its frustrating, astonishing, genuinely mysterious specificity. Not a mystery kept alive by hype or wishful thinking, a mystery kept alive by the data, by the fact that the numbers don't add up in a way that any single explanation fully resolves, and that the object itself is gone, taking whatever it knew about itself into the permanent dark of interstellar space. And somewhere out there right now it's still moving, still tumbling probably, end over end or face to edge in its restless, uncertain way, still wearing its reddish coat of tholins, accumulated over years and light years of interstellar travel, receding from our sun at tens of kilometers per second, slowing ever so slightly as it climbs out of the sun's gravitational influence, but not stopping, not turning, not coming back. It will pass through the outer solar system, through the loose halo of distant icy bodies, and eventually, long after everyone reading or listening to these words has gone, it will cross the boundary where the sun's influence fades entirely into the background of the galaxy, and it will become again what it was before we ever noticed it, an interstellar traveler, a piece of somewhere else, moving through the long dark between stars toward no particular destination, unhurried and completely indifferent to the brief, frantic attention of a small planet it passed on one otherwise unremarkable morning in the autumn of 2017. So there it is. The natural explanations sit in a row, each one doing something useful, each one leaving something unexplained, and the object itself gone permanently beyond our reach. But here is where the story takes a turn that some people found uncomfortable, and others found thrilling, and most planetary scientists found somewhere between premature and genuinely unhelpful, though they said so for the most part in the careful, measured language that scientists tend to use when a colleague has gone somewhere the field is not ready to follow. Because not everyone who looked at ʻOumuamua's data came away reaching for frozen nitrogen or porous dust aggregates. One person looked at the number, the non-gravitational acceleration, the absence of any detectable exhaust, the extreme flatness suggested by that extraordinary light curve, the fact that sunlight pressure alone could actually push a sufficiently thin and light object, and said something that landed in the public conversation like a stone in still water. That person was Avi Loeb, an astronomer at Harvard, one of the most prominent and widely cited astrophysicists in the world, not a crank, not a fringe voice, a person with a long and serious career in mainstream science. And what he said in a series of papers and then in a book published in 2021 called Extraterrestrial was roughly this: we cannot rule out that ʻOumuamua was artificial. Let that settle for a moment. Not that it was probably artificial, not that he was certain, but that the data as it stood was consistent with an object that had been made rather than formed. Specifically, a thin, flat structure, a sail essentially, of the kind that engineers on Earth have actually designed and discussed, a light sail pushed across interstellar distances by starlight the way a sail on water is pushed by wind, a technology that humans have in fact, in a rudimentary way, tested. The Planetary Society launched a small solar sail spacecraft called LightSail 2 in 2019, demonstrating the basic principle. The idea that a civilization sufficiently advanced might use this kind of propulsion over millions or billions of years is not physically absurd. Loeb was careful about that. He was not saying this was definitely alien technology. He was saying the non-gravitational acceleration without outgassing, combined with the apparent thin, flat geometry, was at least consistent with it, and that the scientific community was being too quick to dismiss the possibility without exhausting it. The response from the broader planetary science community was, to put it gently, skeptical. A lot of it was polite skepticism, the kind delivered in footnotes and cautious conference remarks. Some of it was less polite. The general counter-arguments ran along several lines. First, the shape. The extreme light curve variation is real, and it does suggest something with an extreme aspect ratio, but the inference that this means a flat, artificial sail requires a chain of assumptions about how the object was tumbling, its surface reflectivity, and the geometry of our viewing angle, all of which carry uncertainty. A natural body with an unusual shape could produce a similar signal. The flat pancake interpretation, rather than a long, thin cigar, was itself a revision based on later analysis, and each revision depended on modeled assumptions, not direct imagery. We never saw ʻOumuamua, not once. There are no pictures of it, not really. Just a point of light in a telescope image, a dot that moved and changed brightness. Everything else is inference, beautiful and careful and scientifically rigorous inference, but inference. Second, the non-gravitational acceleration. Yes, it is real. Yes, it is measured. Micheli and colleagues published it in Nature in 2018, and the measurement holds. But the conclusion that it requires an artificial explanation depends on the absence of natural alternatives. And as we've been walking through in the last while, the natural alternatives are not empty. They're contested, yes. None of them is fully satisfying. But contested and unsatisfying is not the same as impossible. The hydrogen iceberg, proposed by Seligman and Laughlin, would produce exactly the right kind of invisible push. The nitrogen iceberg from Jackson and Desch would too. A fractal dust structure light enough to be moved by radiation pressure would explain it without any sublimation at all. The fact that we can't confirm these explanations is partly because we don't have the data. It doesn't mean the object was built. Third, and this is perhaps the most important point of all, and Loeb himself acknowledged it, though he drew different conclusions from it, we simply don't have enough data to decide. The observations were brief, noisy, conducted on a fast-moving object that was already receding from us, never imaged up close, never sampled, never visited by any spacecraft. ʻOumuamua was observed for a few weeks, and then the window closed. What we have is a light curve, a trajectory, an acceleration measurement, a set of spectral non-detections. That's it. It is genuinely remarkable that we can infer as much as we have from so little. But it is not enough to conclude that something was built. You cannot leap from "we don't have a clean natural explanation" to "therefore it was made." That leap runs ahead of the evidence. The honest position, the one most planetary scientists land on when pressed, is something like this. Oumuamua is a genuinely anomalous object. It is probably natural because most things are natural, and because natural mechanisms exist that could in principle produce its observed behavior. But we don't know for certain. We can't know for certain with the data we have. The artificial hypothesis is minority contested and not endorsed by the scientific consensus. But it was proposed by a serious scientist working seriously with the available data, and it cannot be dismissed purely on the grounds that it sounds dramatic. It can be dismissed on the grounds that the evidence doesn't require it, and there is a very large difference between those two things. So there is Avi Loeb's argument clearly labelled for what it is: a hypothesis, a minority position, a documented, serious scientific proposal from a credentialed astronomer, not a conspiracy and not a certainty. One possible reading of deeply ambiguous data from a direction that the majority of the field has looked at and said, not yet, not without more evidence, not with this much uncertainty still sitting in the measurements, and Oumuamua is gone. That's the other thing that has to sit quietly in the background of every one of these discussions. If you want to test any of these hypotheses, hydrogen ice, nitrogen ice, fractal dust, artificial sail, anything, you need the object. You need to get close enough to measure it properly. You need a spectrum at close range, a sample of its surface, an image sharp enough to see its actual shape. And none of that is possible because Oumuamua was discovered already leaving, already past its closest approach, already shrinking in our telescopes. By the time we realized what we had, there was no practical way to intercept it. It had a head start measured in weeks and the velocity to go with it. There was no spacecraft ready, no trajectory that could be calculated and executed in time. The window that opened on October 19, 2017, when Pan-STARRS 1 first caught it against the star field at Haleakalā, was perhaps 2 or 3 weeks long before it faded below detection entirely. The witness left the room. We never got to cross-examine it. And that, in some ways, is the most important thing about Oumuamua that any of the scientific papers can tell you. Not the shape or the color, or the acceleration, or the missing tail. The fact that we were too late, that we only noticed something unprecedented and irreplaceable in the last weeks before it was gone forever. All the debate, natural or artificial, nitrogen or hydrogen, disk or cigar, lives in the long shadow of that simple missed opportunity. A mystery sustained not by hype, but by the permanent insufficiency of the data we were able to collect in the time we had. So Oumuamua carries its secret out into the galaxy, and we are left with our models and our arguments and our carefully honest uncertainty. But then about 2 years later, something else arrived, and this time it looked like home. August 30, 2019, Crimea. A man named Gennadiy Borisov was sitting at a telescope he had built himself, a 0.65-meter instrument, smaller than a large bathroom mirror, assembled not in some national laboratory but essentially by hand, the project of a dedicated amateur astronomer with the patience and skill to grind his own mirrors and align his own optics. Borisov ran a private observatory. He had been watching the sky for years, and on this particular night a smudge appeared in his field of view that shouldn't have been there. He checked it. He looked again. He calculated its orbit. The eccentricity came back at around 3.36, not 1001, not 1.05, not even 1.20 the way Oumuamua's had been, 3.36, wildly, extravagantly hyperbolic. A trajectory so steeply curved that no force inside our solar system could have produced it. No planet had flung this thing, no resonance had nudged it into an extreme orbit over billions of years. It came from elsewhere, from very far elsewhere, from the space between stars, a second interstellar object, But this one, and this is the thing that made astronomers exhale and smile and perhaps feel, just briefly, that the universe was being reasonable for a change. This one had a coma, a real, honest coma. A diffuse cloud of dust and gas surrounding the nucleus, the standard, familiar hallmark of an active comet approaching the sun. You could see it in the images immediately. Not a point of light like ʻOumuamua, not a clean stellar dot that only betrayed its nature through orbital mechanics. A fuzzy, faintly extended smudge exactly the way comets are supposed to look. And then, as the weeks passed and the object came in closer and the telescopes got more time on it, a tail developed. A real dust tail swept back by the solar wind and by radiation pressure into that graceful, slightly curved arc that comets have been trailing across human skies for as long as there have been humans to look up and wonder. Gennadiy Borisov, its formal designation, the second confirmed interstellar object in the history of astronomy, was a comet. An unambiguous, textbook, classifiable comet, the kind of thing that planetary scientists knew how to talk about and measure and fit into their understanding of how icy bodies form and behave. Spectroscopic observations picked up the chemical signatures you'd expect. Gases sublimating off the nucleus as it warmed, including cyanide, which is standard comet chemistry and nothing to worry about. There were dust grains in the coma. The tail reflected sunlight exactly the way it should. After ʻOumuamua, after the missing tail, the invisible gas, the impossible acceleration, the collective reaction of much of the planetary science community to Borisov amounted to, thank goodness, something we recognize, something that behaves the way physics says it should, a comet from another star that chose to be, in its broad outlines, a normal comet. It looked like home, as one researcher put it, not because it was from our solar system, it emphatically wasn't, but because it was the kind of thing our solar system makes. A familiar face in a strange place. Gennadiy Borisov, the amateur astronomer who caught it with his homemade telescope, became briefly famous for doing what professional surveys had not yet done, detecting an interstellar comet before its closest approach, giving astronomers weeks of observing time while it was still inbound and brightening, rather than the brief, frantic scramble that had marked the end of ʻOumuamua's visibility. The timing mattered enormously. It meant that every major telescope on Earth and in orbit could be pointed at Borisov while it was still accessible. The Hubble Space Telescope observed it. Spectroscopic instruments on large ground-based observatories dissected its light into chemical fingerprints. Researchers who had been handed only scraps of data for ʻOumuamua now had weeks of high-quality observations to work with. And what they found when they really looked was that Borisov was familiar, but not quite, because even a textbook comet from another star turns out to have a story written in its chemistry that speaks of a very different origin. The most striking signal was carbon monoxide, specifically the ratio of carbon monoxide to water, two of the most fundamental volatiles in a comet's chemical inventory, the things that evaporate and form the coma as the nucleus warms. In a typical comet from our own solar system, this ratio falls within a range. There's variation, and some comets are more co-rich than others, but there's a familiar distribution that reflects where and how objects form in planetary systems not too different from ours. Borisov's ratio was, by the measurements reported by teams, including those led by Denis Bodowitz and Martin Kordner, published in 2020, among the highest ever measured in any comet. The carbon monoxide abundance was extraordinarily high relative to water. Not a marginal difference, not just slightly outside the range, but strikingly noticeably elevated. What does that mean? Carbon monoxide is a molecule that only remains frozen in the very coldest environments. In a comet's nucleus, where different volatiles are layered at different depths depending on when and where they condensed, CO tends to represent the outer system. the regions far from the parent star where temperatures drop low enough for it to freeze and incorporate into an icy body during formation. A comet with a lot of CO relative to water is a comet that likely formed at very large distances from its star in the cold outer reaches of whatever planetary system it came from. It formed far away. It formed in the cold. Which means Gennadiy Borisov, the textbook comet, the one that looked like home, almost certainly did not form the way most of the familiar comets in our solar system formed. It condensed in the frigid outer reaches of a distant planetary system we will never see, under conditions that left their signature baked into its chemistry like a return address with no name attached. It got there, to our skies, to Gennadiy Borisov's homemade telescope, via a journey that probably began in a cold, far orbit around some other star, was somehow perturbed or flung out of that system, and then travelled for what may have been millions or billions of years through interstellar space before crossing our path. And even then, even after all of that, the chemistry remembered where it came from. That's the thing about these objects. They carry their history with them, not in a metaphorical sense, but in a literal molecular sense. The ratios of gases locked in their ice, the colors of their surfaces, the shape of the grains suspended in their comae. Borisov is alien not in its broad structure, which is recognizably cometary, but in the fine print of its composition, the specific proportions of its chemistry, the place its molecules say it formed. The same way that a stone picked up off a foreign beach looks like a stone anywhere, roughly spherical, roughly smooth. But if you grind it up and analyze the isotopes in its minerals, you can often say which geological formation it came from, which river eroded it, which continental shelf it settled on thousands of years ago. The origin is written in the material even when the shape looks ordinary. So Borisov gave astronomers two gifts. One was relief, the confirmation that at least some interstellar objects are perfectly classifiable comets, that not everything coming from outside the solar system was going to be as intractable and anomalous as ʻOumuamua. The solar system is not a singular miracle in the galaxy. Other stars make comets too. Other planetary systems produce icy bodies, pack them into cold outer reservoirs, and occasionally fire them out into interstellar space. That sounds obvious when you say it, but it's actually important to have confirmed. We now knew it, not just suspected it. Borisov was the confirmation. The second gift was the chemical fingerprint, that CO-rich signature, that record of cold formation far from a host star, gave us our first actual measurement of material from another planetary system, not an indirect inference, not a theoretical deduction, but a real measurement on real molecules from a body that formed somewhere else. Comparative planetology, the science of comparing how different planetary systems form and evolve, suddenly had its first data point from outside. Every solar system comet we study before Borisov was data from a sample size of 1. Borisov extended that sample, infinitesimally but genuinely, to something slightly larger than 1, and then its nucleus began to fall apart. In early 2020, as Borisov was making its closest approach to the Sun and then beginning to recede, the Hubble Space Telescope caught something remarkable in its images of the comet's inner coma. There was a secondary condensation beneath a small, distinct brightness concentration near the main nucleus that persisted over several observations and then separated. A piece of the nucleus had broken off, a fragment, small and difficult to measure precisely because it was embedded in the glow of the coma, but real and detectable in Hubble's sharp images. This kind of fragmentation is not unusual in comets. The Sun's heat and the tidal stresses of approaching the inner solar system can split a nucleus, and several comets in our own system have done exactly this. Comet Biela famously split into two pieces in 1846 and was never seen intact again. Shoemaker-Levy 9 fragmented entirely Before striking Jupiter in 1994, the process is understood, but it was strange and somehow moving to watch it happen to Borisov. This object had traveled, by any reasonable estimate, for an inconceivably long time through the darkness between stars. Its nucleus, a few hundred meters across at most, maybe slightly under a kilometer, had held together through that entire journey. The interstellar medium, the faint trickle of radiation, and the rare stray particle had left its mark on the surface, the space weathering that reddens and processes the outermost layers over time. But the body itself had remained intact. And then it came into our solar system, the first we know of, from another star to arrive while we were watching, and the sun's heat began to work on it, and somewhere on or near its nucleus a piece gave way. A fragment of another star's planetary system, breaking apart in our sky, caught in the act by the Hubble Space Telescope. It was gone before the pieces could be studied separately. Borisov was already on its way out, receding from both the Sun and the Earth, fading in the telescopes, and then below the threshold of detection. And then it was over. Like ʻOumuamua before it, like every visitor from outside, Borisov was never going to stay. It came on a hyperbolic trajectory, and a hyperbolic trajectory only goes one direction. It passed through and kept going, but it left something behind. Not physically. There are no fragments orbiting our sun, no debris scattered through our solar system that we can go and collect. What it left was a measurement, a chemical story, a demonstration that interstellar comets are real and diverse and chemically interesting, and that the galaxy produces them and sends them our way, and that we can, if we are lucky and attentive and equipped with the right instruments, actually read what they have to say about the worlds that made them. ʻOumuamua had asked a question and refused to answer it. Borisov asked a question and answered it clearly, with the confident directness of something that had nothing to hide. And then the sky went quiet again, for a little while. And it is here, in the quiet that followed Borisov's departure, that we need to sit for a moment with the stranger of the two, because the contrast between them illuminates something important, and because ʻOumuamua deserves the full, honest treatment it rarely gets. When Borisov arrived, it slotted neatly into a category we already had. Comet, interstellar variety, unusual chemistry, fascinating. We had the vocabulary for it. The instruments knew what to look for. The measurements came back and made sense within a framework scientists had spent decades building. There was a coma, there was a tail, there was detectable gas, including that striking abundance of carbon monoxide, and all of it fit together the way a solved puzzle fits together, the picture on the box and the picture in your hands, agreeing with each other. ʻOumuamua never did that. ʻOumuamua accelerated away from the sun measurably, detectably, in a way that could not be accounted for by gravity alone. The acceleration was real, not a data artifact, not a telescopic glitch. It was documented carefully and published by Micheli and colleagues in Nature in 2018, one of the most scrutinized papers in planetary science of the decade, and it stood up. The object sped up as it left. That part is not in dispute. In a comet, that kind of non-gravitational acceleration is completely normal. Comets are essentially dirty snowballs, and when you bring a dirty snowball near a star, the surface heats up and material boils off. Gas, dust, little jets of volatile ice turning suddenly to vapor. And those jets push the comet the way a slow, untidy rocket engine would push a spacecraft. Momentum is momentum. The comet's own outgassing nudges it measurably off the trajectory pure gravity would predict. So a comet that accelerates is ordinary, expected, boring even to the people who measure such things professionally. But ʻOumuamua showed no outgassing, no coma, no visible dust tail. The Spitzer Space Telescope tried to detect it in infrared, the wavelengths you would expect a dusty body to emit, and found nothing. Deep optical imaging found no haze around it, no cloud of escaping material, no evidence of the exhaust that should have been driving the acceleration. The comet was pushing itself without, apparently, pushing anything out. This is the thing that genuinely puzzled people. This is the thing that keeps the papers coming years later. Not the shape, not the color, not the tumble. Those are unusual, but they are not impossible. The missing exhaust is the problem. You cannot have the push without the substance doing the pushing. Something was escaping ʻOumuamua, or something else was acting on it, and whatever it was, the telescopes of 2017 and 2018 could not see it. Several serious non-alien explanations were proposed by serious non-sensationalist scientists, and it is worth walking through them slowly because they are genuinely interesting and because the debate itself tells you something about how science works at its edges. One idea, developed by Darryl Seligman and Greg Laughlin in 2020, was the hydrogen iceberg hypothesis. What if Oumuamua were made in large part of solid molecular hydrogen, solid H2 ice? If that were true, it would sublimate, turn directly from solid to gas in the heat of the inner solar system, and hydrogen gas is essentially transparent to most of the instruments we used to look for it. The outgassing would be there, driving the acceleration, and we would simply not see it. Elegant, internally consistent. A real solution if the object could be made of such material in the first place. But solid molecular hydrogen is extraordinarily fragile. It does not survive easily. Huang and Loeb, yes, Loeb again, arguing against his own more famous idea for a moment, raised the concern that an He2 iceberg would likely sublimate away during the long journey through interstellar space, exposed to starlight and cosmic radiation over millions or billions of years. Whether such a body could form at all and whether it could survive transit between stars remains deeply uncertain. The hypothesis is clever, it may be right, it is not settled. Another idea came from Alan Jackson and Stephen Desch in 2021, the nitrogen iceberg, sometimes called the cosmic Pluto hypothesis. In our own solar system, Pluto and similar Kuiper Belt objects have surfaces partly composed of solid nitrogen ice. If a collision in another planetary system had chipped a piece off the frozen nitrogen surface of a Pluto-like world and ejected it into interstellar space, that piece might look something like Oumuamua. Solid nitrogen is highly reflective, which would make the object bright for its size, consistent with the observations, and sublimating nitrogen would push it without producing a visible dust tail, because nitrogen ice is clean in ways that water-rich cometary ice is not. Critics, including Loeb and Amir Siraj, pointed out a problem with abundance. To produce interstellar objects like Oumuamua in the numbers we would need to account for, given how rarely we catch them and how many we must therefore be missing, you would need a very large amount of nitrogen ice being scattered across the galaxy. More perhaps than the known population of Pluto-like bodies across all the star systems in the Milky Way could plausibly supply. The numbers did not comfortably work. The hypothesis remains possible, it is also not settled. Other ideas circulated. An ultra-low-density fractal aggregate, a structure so porous, so fluffy, more like a loosely packed cloud of tiny particles than a solid body, that radiation pressure from the sun could push it directly the way sunlight pushes a solar sail, and the fractal structure might scatter gas in ways that evaded our detectors. Also interesting, also not confirmed. And then there was Avi Loeb. Loeb is a Harvard astronomer, a real one, a serious one, with a long career in astrophysics well before Oumuamua, and in 2021 he published a book called Extraterrestrial in which he argued that the combination of the anomalous acceleration and the flat, potentially pancake-like shape of the object was consistent with a thin, artificial structure pushed by sunlight. A light sail, not necessarily a crude vehicle, not a Hollywood flying saucer, but possibly a piece of defunct technology, a probe or a sail built by some civilization somewhere and now drifting, dead or dormant, through the galaxy. It is important to say this clearly and without sneering. Loeb is not a crank. He made an argument based on the documented anomalies, and he made it in public, which took a kind of professional courage that is easy to underestimate. The artificial probe hypothesis is a real hypothesis made by a real scientist about real data. It is also important to say with equal clarity that it is a minority position. The majority of planetary scientists and astronomers who have engaged with it consider a natural explanation more likely, even if no single natural explanation has yet closed the case cleanly. The hypothesis is contested vigorously. And the fundamental, uncomfortable, honesty-demanding fact at the center of everything is this: we do not have enough data to be certain either way because ʻOumuamua is gone. It was discovered after its closest approach to the Sun, already on its way out. The window for observation was roughly 2 to 3 weeks, brief, and the images were never close up. No spacecraft intercepted it. No probe was ever in a position to approach. Every model, every paper, every hypothesis, the hydrogen iceberg, the nitrogen chip, the fractal cloud, the light sail, rests on that slim, fast, distant set of measurements from 2017. The witness left the room before the interview could begin. This is not a rhetorical flourish. It is the actual epistemic situation. The case cannot be closed with the evidence we have, because the evidence we have is all we will ever have. ʻOumuamua is somewhere in interstellar space now, receding at tens of kilometers per second, and it is never coming back, and we will never image it up close, and the mystery it left behind is a permanent fixture of the scientific record until something else. Another visitor, a better theory, a piece of physics we have not yet discovered, resolves it by proxy. That is a strange and somewhat humbling position for science to be in. Not wrong, just genuinely open. And the openness is real, not performed. And then the second visitor arrived. Gennadiy Borisov was not a professional astronomer. He was an amateur working with a telescope he had built himself, a 0.65-meter instrument, modest by the standards of survey telescopes, but carefully made and carefully used at an observatory in Crimea. On the 30th of August 2019, he was scanning the sky when he noticed something that did not move the way solar system objects move, something on a trajectory that did not belong here. The confirmation came quickly. Within days, the orbital calculations were clear. Another interstellar visitor, the second in recorded history, arriving less than 2 years after the first. And this one, immediately, obviously, was a comet. There was a coma, a fuzzy halo of gas and dust surrounding the nucleus. There was a tail. The spectrographs found gas. The whole apparatus of cometary science snapped into place around it the way it is supposed to, and astronomers who had spent years puzzling over ʻOumuamua's missing exhaust exhaled something close to relief. Here was a thing that behaved the way a thing from outside the solar system was supposed to behave. Here was the normal case. Here was the baseline. It looked like home in the sense that it looked like the comets our own solar system produces, but with a chemical twist that made it something else entirely. The measurements of its composition, led by Bodowitz and Cordiner and their colleagues and published in 2020, showed that Borisov carried an unusually high abundance of carbon monoxide relative to water, among the highest ever measured in any comet. Not just high for an interstellar object, high by any standard, a ratio that pointed toward a specific kind of origin. Carbon monoxide is a volatile molecule. It freezes at very low temperatures and is preserved in the cold outer regions of a planetary system far from the warmth of a star. A comet rich in carbon monoxide relative to water is a comet that formed in the cold, that condensed in the distant outer reaches of whatever system gave it birth, far from whatever sun it once orbited. Borisov's chemistry was, in this sense, a fingerprint of its origin. The object had formed far from its star, in conditions colder and more remote than the environments that produce most of the comets we see in our own solar system. So even the normal interstellar comet, the one that played by the rules, the one that looked like home, even that one carried the mark of somewhere else. Even the familiar one was, on close reading, alien. And it was fragmenting. As Borisov neared the Sun in early 2020, the Hubble Space Telescope observed something happening to its nucleus. A piece was breaking off. The nucleus of Borisov was estimated at well under a kilometer in size, a few hundred meters perhaps to something approaching a kilometer at the outside, small even by cometry standards. And the tidal and thermal stresses of approaching the Sun were more than part of it could withstand. A fragment detached visibly, caught in Hubble's imaging. A piece of another star's planetary system coming apart in the heat of our star. And then the third one came. It arrived on July 1st, 2025, not at a famous observatory on a Hawaiian mountain, not through the careful eye of an amateur astronomer working alone in the night. It was found by a survey telescope in the Atacama foothills. The Atlas Survey, which stands for Asteroid Terrestrial Impact Last Alert System, at its station in Río Hurtado, Chile. A system built specifically to sweep the sky, automatically, methodically, looking for things that don't belong. And on that July night, it found something that didn't belong at all. Its formal designation is 3I 2025N1, also catalogued as C 2025N1. But most people who heard about it came to know it simply as 3I Atlas, the third interstellar object ever detected, the third visitor from outside our solar system in just 8 years. If you're still listening from wherever you are tonight, still warm, still quiet, let that number sit for a moment. 3. 3 confirmed objects from other star systems. For all of recorded human history, before October 2017, the count was 0. We had watched the sky for centuries, built telescopes and catalogues and careers out of understanding everything that moves above us, and we had caught nothing from beyond. Then, in the span of time it takes a child to finish primary school, we found 3. But let's not rush. That's not what this particular hour is for. 3I Atlas was a comet. Not ambiguously, not with asterisks. It developed a coma, that fuzzy atmosphere of gas and dust that forms when a comet's ices begin to warm and sublimate before it even reached its closest point to the Sun. That mattered. A coma before perihelion means the object was already outgassing from a significant distance, which means it had volatile material in abundance, and which means it was behaving exactly as a natural comet should behave. The very quality that ʻOumuamua conspicuously lacked, visible activity, a real coma, evidence of the ordinary physics of cometary sublimation, was on full and clear display here. It was also comparatively large, considerably larger than ʻOumuamua, which had been estimated somewhere in the range of 100 to 400 meters in its longest dimension. The nucleus of 3I Atlas carried early upper bound estimates of several kilometers, though refined analysis pulled the solid nucleus smaller, with the surrounding activity and coma inflating the apparent size in the telescope images. Even accounting for that, even being conservative, it was markedly bigger and brighter than the first visitor. That was part of why so much telescope time could be devoted to studying it. A bigger, brighter, actively outgassing comet on a predictable trajectory is a gift to astronomers. You have time, you have signal, you can actually look at the thing properly, and people looked. There were reports of unusual features in the early spectra. signals in the carbon dioxide and carbon monoxide range, and something that drew particular attention, what appeared to be nickel in the early spectroscopic readings, without the usual accompanying iron signal. It is worth noting carefully here that early spectroscopic results from fast-moving objects are always subject to revision. These are measurements taken quickly, sometimes under competitive pressure, from a target that is continuously changing position, brightness, and distance. The first read is rarely the final word. But the nickel without iron observation was the kind of thing that makes chemists and planetary scientists pause, because it was slightly unlike the pattern you typically see in solar system comets. And slightly unlike is always interesting when the object in question came from somewhere else entirely. There was also, at one stage, excitement about what was described as an anti-tail, a feature that appeared to point toward the Sun rather than away from it. Normally, comet tails stream behind the comet in the direction away from the Sun, pushed there by the solar wind and radiation pressure. An anti-tail sounds like a paradox. It sounds like evidence of something strange, but it isn't really. It's a geometric and perspective effect. When large dust grains are ejected from a comet's nucleus, they can drift along the comet's orbital path rather than streaming directly behind. If you observe the comet from a particular viewing angle, specifically when Earth crosses the plane of the comet's orbit, those dust grains appear projected forward toward the Sun as a kind of sunward spike or anti-tail. It is not a violation of physics. It doesn't require an unusual explanation. It's an optical geometry, a matter of where you're standing when you look. The anti-tail of 3I Atlas had a natural explanation, like most of the features that prompted early excitement. It was a comet doing comet things, seen from a particular angle. What it was not natural to say, and what required a different kind of looking entirely, was something else. Because it was large and bright and strange in origin, and because we live in a time when the question has been loudly asked before, someone was always going to ask it about 3I Atlas too. And someone did. Avi Loeb, the Harvard astronomer who had argued publicly that Oumuamua's unexplained acceleration and possible sail-like shape were consistent with an artificial light sail, a defunct piece of alien technology pushed by sunlight, turned his attention to the third visitor as well. He noted the trajectory, the size, the timing, the early chemical oddities. He raised the question of whether this too warranted consideration as something more than a natural comet. He asked the question openly, as he had done before, as a provocation designed to take seriously what others were inclined to dismiss, and so people listened, not metaphorically, literally. Radio telescopes were pointed at 3I Atlas. The effort included work associated with the Breakthrough Listen program, the largest ever scientific research program dedicated to searching for technosignatures, signals that would indicate the existence of artificial, technologically produced transmissions. Facilities including the Allen Telescope Array, an array of radio dishes designed specifically for this kind of listening, were directed at the comet as it moved through the inner solar system. The search was systematic. The question was simple and precise. Is this object emitting any artificial radio signal? Any pattern that couldn't be explained by natural processes? Any transmission? The answer was clean. Nothing. No signal, no transmission, no pattern that required an artificial source. The object was silent in every frequency that was checked. It behaved in the radio spectrum exactly as a natural comet behaves, which is to say, it didn't behave at all because natural comets don't talk. The SETI scan returned a null result, as clear and uncomplicated as results in this field ever get. And here is why that null result matters, not as a disappointment, but as information. The artificial probe hypothesis, whether applied to Oumuamua or to 3I Atlas, lives partly on the argument that we haven't ruled it out. That absence of evidence isn't evidence of absence. that our instruments might not detect something sufficiently advanced or sufficiently quiet. These are fair philosophical points, and they're worth taking seriously as general epistemology. But they are not the same as evidence. They are not the same as a positive signal. When you aim the best listening equipment we have at an object and hear nothing, not faintness, not ambiguity, not a maybe, but nothing, that is meaningful data. It doesn't prove the object is natural, but it adds to the weight on that side of the scale, and it adds it clearly. 3I Atlas was, by every measure available to us, a comet. A large, ancient, actively outgassing comet from somewhere beyond our solar system, moving on a hyperbolic trajectory that would carry it through and out again, never to return. And it was ancient in a way that takes a moment to absorb properly. The work on 3I Atlas's age and origin, work associated with Matthew Hopkins and the Otautahi Oxford team, published in 2025, placed the object's origins in the Milky Way's thick disk. That phrase sounds technical, and it is, but what it means is genuinely remarkable. Our galaxy, the Milky Way, has layers. There is a thin disk, which is relatively young, where most of the active star formation happens, where you find younger stars with higher concentrations of heavier elements. And there is the thick disk, older, more diffuse, populated by stars that formed earlier in the galaxy's history when the universe was younger and the composition of star-forming gas was different. The thick disk is a record of an earlier epoch. It's where the old galaxy lives. 3I Atlas, according to this dynamical modeling, came from there, from that older population. And the age estimates that followed from this were staggering. The headline figures from the modeling were roughly 3 to 7 billion years, with outer bounds discussed up to approximately 11 billion years. For a moment, hold what that means alongside the familiar number of 4.6 billion years. The age of our own solar system, the Sun, the Earth, the Moon, the rest of the planets. Everything we live on, everything we have ever observed directly, everything that has ever existed in human experience exists within a system 4.6 billion years old. 3I Atlas, if the modeling holds, may have been wandering the galaxy since before any of that existed. If the higher estimates are correct, this object could have been drifting through interstellar space since before the Sun ignited. Since before the cloud of gas and dust that would become our solar system even began to collapse. It formed somewhere in some ancient planetary system around some ancient star in an era when the galaxy looked different, when the stars that made it were older generation stars, and when the cosmic abundance of heavy elements was different, and when nothing that would become us had yet begun. It then separated from whatever system gave it birth, perhaps through a gravitational interaction with another body, perhaps through the slow dispersal of a dying system, and it entered the interstellar void. And it has been traveling ever since, for billions of years, longer than the Sun, longer than Earth, longer than anything living. This is what people mean when they say galactic archaeology, not a metaphor, not a poetic flourish, a genuine fossil, a frozen time capsule from an earlier epoch of the galaxy, preserved in the cold between stars, arriving at our doorstep in July 2025, discovered by a camera in the Chilean hills. If you needed a reason to feel the strangeness of what we're living through right now, of this particular moment in the history of astronomy, this is it. We caught a comet older than the Sun. It made its closest approach to the Sun, perihelion, in late October 2025, passing inside Mars's orbit. And then it made its closest approach to Earth in December 2025. Both of these events sound alarming if you encounter them in a headline without context. Something that old, that large, coming that close. But the distance involved was completely safe. It never threatened the Earth in any physical sense. There was no impact risk. The closest approach geometry was a viewing opportunity, a positioning that allowed telescopes around the world to study it at their best available resolution. not a threat, and people did study it. Through that October and into December, observatories tracked it, photographed it, measured its spectrum, tried to understand its chemistry, because if you have a frozen relic of the early galaxy passing through your neighborhood, and you have the instruments to read its composition, the reasonable thing to do is read everything you possibly can. What those readings will ultimately tell us is, as of this narration, still being assembled and revised. Early science is always like that. The picture builds slowly, peer by peer, but what was already clear was the outline, a natural comet, ancient, from the thick disk, carbon-rich, chemically interesting, naturally explained, and then it left. On its own hyperbolic trajectory, moving with an orbital eccentricity reported above 6, far, far above the threshold of one that marks the boundary between bound and unbound, it left the inner solar system as all three visitors have left, on a path the sun's gravity cannot bend back. It is gone the way ʻOumuamua is gone, the way Borisov is gone. We will not see it again. No telescope in history will catch it a second time. It joined the permanent, unreachable file, and now we had three. 3 interstellar objects confirmed in 8 years, 3 permanent additions to the record, 3 visitors from other star systems that we actually detected, measured, and documented. And it is now, with all 3 in hand, that the real story becomes visible, not the story of any single object, but the story of what they are together. Because here is what 3 objects tell you that one object cannot, and that 2 objects only begin to suggest. They are different from each other, genuinely, substantively, fundamentally different, not variations on a theme, not the same kind of thing with minor surface variation. 3 objects, 3 characters. ʻOumuamua, small, somewhere between 100 and 400 meters. Dry-looking, no visible coma, no dust tail, no detectable gas escaping it at the sensitivity of our instruments. Tumbling in a chaotic rotation roughly every 8 hours, varying in brightness by a factor of about 10, implying an extreme shape unlike any solar system body we had seen. Moving with a non-gravitational acceleration it had no business having. The reddish color of long space weathering, the Spitzer Space Telescope unable to find it in infrared, the great unresolvable oddity. 2I Borisov, also small by cometary standards, a nucleus of a few hundred meters to perhaps a kilometer, smaller than many solar system comets, but otherwise unmistakably a comet. Coma, tail, detectable gases, visible fragmentation, recognizable, familiar in structure, alien only in its carbon monoxide richness, a fingerprint of cold outer system origin, a comet that played by the rules and still told you something about where it came from. 3I Atlas, larger, brighter, older than the Sun in some models, from the thick disk of the galaxy. A comet with an active coma before perihelion, early chemical oddities in its spectrum, a natural antitail explained by geometry, and a perfect silence in the radio frequencies. Ancient, enormous by comparison to its siblings, natural, unrepeating. 3 visitors, 3 completely different profiles. If you had sent a scientist from another civilization to study them expecting a unified type of object, a category, a population of similar things, they would have been confused. The range is too wide, the characters are too distinct, and this is precisely the point. This is the headline scientific lesson that gets lost when we focus only on the oddest of the 3. The galaxy does not throw one kind of thing, it throws everything. Every planetary system that has ever formed, and there are hundreds of billions of stars in the Milky Way alone, many of them with planets, most of them with leftover material from the processes of formation, every one of those systems sheds debris. Comets ejected by gravitational interactions, icy chunks thrown outward and inward as giant planets migrate. fragments of surfaces struck by impacts and sent spinning free. All of that material, every piece of it, is traveling endlessly through the dark between stars on trajectories that occasionally, by chance, bring them through a neighborhood like ours. And what we get when we intercept them is a sample of the other solar systems. Not a proxy, not an inference, not a model result from someone's computer simulation. A literal piece of the thing, a chunk of material that condensed in the disk of another star that formed in those specific temperatures and pressures and chemical abundances that has been preserved in the cold ever since. Borisov's carbon monoxide abundance told us about the cold outer regions where it formed. 3I Atlas's age and thick disk origin told us about an earlier epoch of the galaxy's star-forming history. Even ʻOumuamua, even the mystery, the unresolved oddity that we cannot cleanly classify, told us something, that at least some interstellar objects defy the categories we bring to them, that nature has had billions of years in billions of places to create things that don't fit our local taxonomy. Each one is a free sample delivered to our doorstep. Comparative planetology at no cost across distances that no spacecraft could ever cover. But there is a question buried under all of this that matters as much as the science, and it's the one that the pattern of detection forces you to ask. If we caught 3 in 8 years, in the specific 8 years after our survey telescopes became sharp enough to do this, how many have we been missing? For all of human history before 2017, the interstellar object count was 0. Not because they weren't there, not because none had passed through, because we couldn't see them. Our telescopes, our surveys, our cadences of observation, none of it was optimized for catching fast-moving, faint, slightly unusual objects crossing the solar system on one-way paths. The instruments we had simply weren't looking at the right things with the right frequency and the right depth. And so they passed. An unknown number of them, one after another, through the inner solar system, past the orbit of Earth, around the Sun, and out again. Undetected, unnamed, gone. Estimates suggest that at any given moment, on average, roughly 1 interstellar object may be present somewhere in the inner solar system. Close enough, in principle, to observe. One object that formed around another star here, now somewhere in the region of space we can watch. One object at a time, and we have been unaware of this for our entire existence. The 3 we found in 8 years are almost certainly a small fraction of the objects that actually passed through during that period. The detection efficiency for something like ʻOumuamua, small, faint, discovered only after its closest approach had already passed, is very low. We are not catching everything. We are catching the brightest, the most favorably positioned, the ones that happen to cross a survey telescope's field at the right moment. The rest pass through silently, observed by no one. But that is beginning to change. The Vera C. Rubin Observatory, located in the Andes of Chile, is the next generation. It runs the Legacy Survey of Space and Time, LSST, an unprecedented all-sky survey program that will image the entire visible sky every few nights, down to extremely faint magnitudes, building up a continuous deep record of everything that moves. It is already transforming what it means to survey the night sky, and for interstellar objects its implications are extraordinary. Where Pan-STARRS caught ʻOumuamua more or less by chance, and the Atlas survey caught 3I Atlas by design, but with limited sensitivity, the Vera C. Rubin Observatory will catch interstellar objects routinely, not 1 every few years, not 2 in 8 years, potentially dozens over the course of its survey lifetime, possibly more. The models of detection rates, adjusted for Rubin's capabilities, suggest a genuine flood is coming. Not a flood of once-in-a-lifetime anomalies, a flood of catalogable objects, a studyable population. Think about what that means for a moment. Right now, ʻOumuamua is a mystery, partly because it was one object, observed briefly, never imaged, already leaving when we found it. There is no comparison population. We have one data point for the weird, anomalous, accelerating, coma-free variety, and we cannot know whether that's a category of object, whether there are others like it out there, or a true one-off. One data point tells you almost nothing about how common something is. But if Rubin finds dozens of interstellar objects over the coming decade, and even a handful of them show the kind of anomalies ʻOumuamua showed, the non-gravitational acceleration, the extreme shape, the absence of visible outgassing, then we begin to understand. We start to know whether ʻOumuamua represents a class of object we hadn't encountered before, a genuinely unusual but naturally occurring type, or whether it was a statistical outlier even within the interstellar population. We start to build the frequency table, and frequency tables in science are the foundation of understanding. We are entering an era where interstellar visitors stop being events and become data. And beyond the Rubin Observatory, there is another instrument being prepared, not for surveying, but for rendezvous. The European Space Agency is developing the Comet Interceptor mission. Its planned launch is around 2029, and its concept is unlike anything flown before. The idea is that rather than being sent toward a predetermined target, the spacecraft will be placed in a waiting position, parked, in effect, at the gravitational equilibrium point between the Earth and Sun, known as the L2 Lagrange point, and it will wait for a new comet to be discovered. A fresh, long-period comet falling in from the distant outer solar system for the first time. Or, if luck and timing align, something even rarer, a confirmed interstellar object on a good approach trajectory. When such a target appears, the mission can be directed toward it with enough lead time to actually intercept it. Not a distant observation, but a hopeful inference from a light curve, an actual flyby, a spacecraft arriving at the comet with cameras, spectrometers, dust collectors, instruments designed to look at the surface, sample the environment, read the chemistry directly. The kind of up-close encounter that ʻOumuamua never gave us because it was already gone when we found it. Whether Comet Interceptor will get an interstellar target is not guaranteed. It's an opportunistic mission and the universe does not cooperate with schedules, but it is designed in part with that possibility in mind. The fact that we are now building spacecraft that sit and wait for interstellar objects to arrive, that these are not hypothetical targets but a recognized category of mission objectives, says something profound about how quickly the field has changed. 8 years ago, the Interstellar Object Catalogue was empty. Now it has 3 entries, a ground-based survey capable of finding more, a next-generation telescope that may find dozens, and a spacecraft in development to finally photograph one up close. This is what a field looks like when it goes from theoretical to observational. When something that lived only in equations and speculation becomes a physical object you can point a telescope at. And when you put the 3 visitors side by side, when you hold all 3 of them in mind at once, something shifts in how you understand what they're telling you. It is not about any one of them. It was never really about any one of them, even the strange one, even ʻOumuamua. The story was always about the category of things that leave their home systems and travel between stars. The category that we have now confirmed is real and populated and passing through our neighborhood constantly, invisibly, most of the time unobserved. ʻOumuamua will remain the outlier, the anomaly, the object that broke the textbook in 8 different ways at once and then left before we could figure out how. The natural explanations, the hydrogen iceberg, the nitrogen chip, the fractal dust aggregate pushed by radiation pressure, the undetected trace outgassing, each explains some features, but none explains all of them cleanly. And the honest scientific position remains that we don't have enough data to be certain, and we may never have enough data to be certain because the object is gone and was never imaged, and the brief observational window closed in late 2017 and nothing will reopen it. That unresolved quality is not a failure. It is a feature of doing science on a universe that does not wait for us to be ready. Sometimes the witness leaves the room before the examination is complete. Sometimes the evidence is partial and the verdict is suspended and the case stays open on the shelf. ʻOumuamua may stay on that shelf permanently, and that is a legitimate outcome. Genuinely unexplained things exist. The appropriate response to a genuinely unexplained thing is not to pick the most exciting explanation and declare it solved. It is to hold the uncertainty honestly, to keep improving the models, and to watch for more objects that might eventually tell you what kind of thing this was. The other two, though, Borisov and 3I Atlas, are not mysteries in that sense. They are understood in the ways that matter. Natural comets, chemically distinctive, ancient, each carrying the fingerprint of somewhere else, somewhere we will never visit, somewhere we can now taste from our own backyard. Borisov formed in the cold outer reaches of a foreign planetary system, rich in carbon monoxide, slightly fragile in its small nucleus, close enough to textbook that it was almost comforting. A comet that traveled light years and arrived looking recognizable. It told us the recipe for building comets is not entirely alien, that the physics and chemistry that operate around other stars produce things not entirely unlike the things they produce around ours. 3I Atlas formed even earlier, possibly before the Sun existed at all, in an older part of the galaxy, in a thicker and more ancient stellar population, and it preserved whatever chemistry it formed with for billions of years in the vacuum between stars. It arrived large, bright, active, and silent in the radio spectrum, a relic, a genuine galactic fossil. And ʻOumuamua, the first, the one that started all of this. The one that forced the IAU to create a new naming convention overnight, to add an entirely new class to the catalogue of solar system objects, to acknowledge that the sky contains visitors we had never properly prepared for. Small, reddish, tumbling, shaped like nothing in the textbook. Accelerating without exhaust, discovered already leaving. Gone. It arrived in 2017 and it fundamentally changed what we understand ourselves to be living in, not on a planet in a solar system in a galaxy, on a planet in a solar system in a galaxy that is full of the debris of other solar systems, material from other suns, objects that have been traveling since epochs we can barely imagine, passing through constantly, carrying chemistry we have not catalogued, histories we cannot fully reconstruct. We live in a busier neighborhood than we knew. And that is the true strange gift of all three together, not the mystery of any one of them, but the revelation of the whole, the revelation that this is real and ongoing and common and not ending, that the three we've found are not the last, that the Vera C. Rubin Observatory is already watching, building the survey, preparing to catch what comes next, that somewhere between 2017 and now, undetected, objects we never found have already made their closest approach and already departed. That right now, as you listen from wherever you are tonight, there may be another one somewhere in the solar system. Another interstellar object, perhaps, on its way in or already on its way out. Too faint, too fast, too small for the instruments we currently have, but real and moving and carrying something of another world. The galaxy has been sending us postcards for billions of years. We have only just learned to read them, and there is something in that. Something in the smallness of that realization, in the fact that all it took was a slightly better camera and a slightly more systematic sky survey, not a rocket ship, not a radio signal from an alien civilization, just looking more carefully at a sky we thought we knew. Something in that worth sitting with as you drift off tonight. You don't need to travel to find the universe bringing itself to you. It always has been, we were just not looking carefully enough. 3 objects in 8 years, a comet smaller than a city block that moved like a ghost and left a question no one can close, a comet that looked like home and smelled of cold outer darkness. A comet, older possibly, than the sun. A frozen message from before the Earth existed, from before the gas cloud that became all of this had even begun to collapse. All of them gone now, all of them carrying on into the dark between stars, on trajectories so hyperbolic the sun's gravity is barely a ripple. All of them heading somewhere we can't follow, in a universe that is vast enough that even something moving for billions of years barely crosses it. But they came through here, through our little warm corner of the galaxy, through the very patch of space where you are lying right now, wherever that is. If you are in the northern hemisphere, somewhere in the autumn sky of a year or two ago, ʻOumuamua passed. If you could have gone outside on the right night and known exactly where to look, you would have seen nothing with the naked eye. It was far too faint, but it was there. A reddish, tumbling piece of somewhere else in your sky.
And Borisov, and 3I Atlas. You are in the solar system. The solar system is the neighborhood the Milky Way brings its wanderers through. You were always here for all of this, whether or not you knew it. The visitors were always passing. We have just begun to notice them.
Earlier tonight, at the very beginning of all of this, I asked you where in the world you're listening from. And I meant it genuinely, and I do think about that. The specific corners of the world and the night that bring people here. Maybe you're in a city where the sky above you is washed orange with light and the stars are invisible, and the idea that objects from other star systems are passing overhead feels very distant from the bed or the couch or the chair where you've settled in. Maybe you're somewhere dark, somewhere you can actually see the stars, and the sky outside your window is the actual Milky Way, thick with them. Either way, you are in the same solar system. You are under the same neighborhood sky. And this particular neighborhood, it turns out, receives visitors from other systems. Ancient frozen objects, remnants of worlds we will never map, made of ices that condensed around stars whose names we don't know, whose planets we have never seen. And they pass through silently, and they leave. And if we are looking in the right way at the right moment, we catch them briefly, and we read what we can from them before they go. We are part of the galaxy in a more literal sense than most people mean when they say that. Not metaphorically woven into the cosmos, actually physically in the path of objects that originated in other parts of it, receiving material from other star systems on a regular ongoing basis. Participants, however passive, in a kind of galactic exchange. If you enjoyed this slow journey tonight, through ʻOumuamua's tumbling mystery, through Borisov's familiar strangeness, through 3I Atlas's ancient silence, a quiet like or subscribe would mean a great deal. Small creators like me really do rely on your support to keep this going, to keep the next journey available for the next night. And I would love to know where you are listening from tonight and what time it is in your corner of the world. Leave it in the comments when you can. I read them. The stars are still up there, wherever you are. The galaxy's thick disk is still rotating slowly, carrying its ancient stars and their ancient debris. And somewhere out there, on a hyperbolic trajectory curving gently away from the sun, 3 small cold objects from other worlds are continuing their journeys. Journeys that began before most things in this solar system existed, that will continue long after most things end. You saw them pass, in a manner of speaking. You were here for the 8 years that changed everything. That's a good thing to carry into sleep. Stay as long as you like in Nightoria. Good night.